Okay, welcome back to this new edition. Today we are going to continue with the next part of the center regional mock proposed by a student on our YouTube channel. So here's the B question of the paper 6B. So this question 6B of the center regional mock. I'm going to place a link to the whole paper on the description so that if you don't have the questions, you can get a look at the physics questions on the from the paper. Okay, now the question reads: the graph in figure 3 shows how the maximum kinetic energy E of photoelectrons emitted from the surface of aluminum varies with the frequency F of incident radiation. So that's the graph I've seen. That's figure 3. Now explain why no photoelectrons are emitted below the frequency of 10 times 10 to the power 4 Hz. So what do we see? This 10 times 10 to the power 4 Hz. So below there is nothing. It means that this frequency F, it is because the frequency below 10 is less than the threshold frequencies, and so no electrons can be emitted, since the condition for electrons to be emitted is that F should be greater than or equal to F naught. And also at the from 0 to 9.99999, what we also realize is that the energy of the incident radiation is less than the work function, so hence no electrons can be emitted since the conditions are not met. So those are the two things we can see. And for electrons to be emitted, E should be greater than or equal to the work function. Okay, Roman 2 says calculate the work function of aluminium in electron volts. So what's work function? W naught or phi is equal to H F naught, where H is the Planck's constant, which is 6.62 times 10 to the negative 34 joule second, times the F naught. F naught is the minimal frequency in which electrons starts being ejected, and from the graph it is 10 times 10 to the power 14 Hz. So we have to leave our answer in electron volts. So we have 6.62 times 10 raised to the negative 34. That will be times that will be multiplied by 10 times 10 raised to the 14. So this gives us 6.62 times 10 to the negative 19 joules. Now, but to convert this in electron volts, we divide by phi in electron volts. We are simply going to divide this 6.62 times 10 to the negative 19 divided by 1.6 times 10 to the negative 19. So if you take 6.62 divided by 1.6, it will give us approximately 4.14 electron volts. So that's the work function of our metal in electron volts. Now what do we have next? State the quantity represented by the gradient. So it's a plot of E in electron volts against F. So what do we know? If energy is incident on the metal surface, that's Roman 3. So this is Roman 2. Roman 3. If energy is incident on the metal surface, then E will be equal to W naught plus K E max. Okay, so since E is in electron volts, now we can see from here we have we plotted the graph of the kinetic energy. Oh wow, that's E is kinetic energy. So we plotted the graph of kinetic energy against frequency. So K it will be equal to E, which is HF, minus the work function. So this is in the form Y is equal to mx plus C, with C equal negative W. So what do we have? M is clearly the Planck's constant. So they state the quantity represented by the gradient of the graph, the Planck's constant. Add a second graph or add a second line to the graph to show how E varies with F for a metal which has a work function less than that of aluminium. So indicated here, we don't know the work function, but since the work function is less than that of aluminium, it means our graph should be somewhere here, parallel. So if this was the line continuing, you see we can extrapolate this with something like this, and this will be something like this. So you clearly see that this work function is less than this. So that's definitely it. Okay, so that's what we have for the first questions. Now C says a tiny drop of mass 1.1 times 10 to the negative 12 kilogram and charge 3e suspended in a gap between two parallel metal plates. The separation between the plates is 10.68 millimeters. Calculate the potential difference between the plates in kilovolts to the nearest kilovolts. Okay, so that's C. So we're on question 6C. What do we have? We have two plates. I'll keep my plates like this, and I have my drop which is between two. So I'm going to call this a positive plate and that's a negative plate. So that's the direction of my field, and this is the weight mg. Now the magnitude of the electric force which opposes the field, so I have EQ, should be equal to mg. So but E is equal to V on D. So we'll say but E is equal to V divided by D. So this means we are going to have V all over D, all of this times Q. This will be equal to mg, and so the potential difference V will be equal to mgd divided by Q. Now the what's Q? Q is 3e. So from here we have V. Let's do numerical application. What's the mass of a drop of oil? It's 1.1 times 10 to the negative 12. 1.1 times 10 to the negative 12 times 9.81 times the separation of the plates D. So the separation of the plates is this D, which is 10.68 millimeters. That will be 10.68 times 10 to the negative 3 divided by times 10 to the negative 3 divided by Q, which is 3e. So that's 3 into 1.6 times 10 to the negative 19. So therefore V will be equal to, so let's punch that and see the value of our potential. Okay, times 10.6 okay, so note this value somewhere, 23.83. Then we sum their powers. So we have 23.83. That will be 2.38 times 10 to the power 5 volts. So that's what we have. But the question asks us to leave it in the nearest whole number. So we are going to put that in the nearest whole number and see what we are going to get. So what do we have here? So we'll write it to the nearest kilovolts. So this is about V will be equal to 238 nearest. Okay, so 238 times 10 to the power 3 volts, so this will be 238 kilovolts. Yes, so that's it in kilovolts, and that will mark the end of this video. So see us in our next video. Stay tuned.